Welcome to today's statistics tutorial. Today we're looking at hypothesis testing with one sample. See the links below for the online calculator we will be using in this tutorial, as well as additional supports and resources.
Hypothesis testing with one sample, and then next week or starting on Wednesday, we will have the hypothesis testing with two samples. So hypothesis testing is this, it's a system to determine if a claim is statistically sound. And the way we do hypothesis testing is we're going to set up two contradictory hypotheses. We're going to set up a H0, which is called the null hypothesis, which is a statement that is believed to be true. And then we're also going to set up an alternative hypothesis, which is going to be the opposite. And that can be either written as HA or as H1. And this is going to be the alternative. It's called the alternative hypothesis, and it's the opposite of the null hypothesis, or what would be concluded if the null hypothesis is rejected. So what you're going to do is you set up your two hypotheses, then you're going to examine the data, and then based on what the data tells you, you're either going to reject the null hypothesis if the sample data favors the alternative hypothesis, or you're going to have a do not reject the null hypothesis or decline to reject the null hypothesis if the information is insufficient to reject the null hypothesis. We don't ever use true or false statements because we're dealing with estimates and probabilities, so we can't say the data makes the null hypothesis true. All we can say is whether or not the data tells us to either reject or not reject the null hypothesis, or what we believe to be, what we're claiming to be true. Your null hypothesis is always going to have an equal. So when we're setting up the null hypothesis, we're going to use equal, greater than or equal to, and less than or equal to. And with the alternative hypothesis, we're going to use does not equal, greater than, or less than symbols. But you're always going to have the equal is going to be connected to the null hypothesis. So let's take just a look at what some of these might look like. Okay, so here's some examples. The first one would be for our null hypothesis. We'd say no more than 30% of the registered voters in Santa Clara County voted in the primary election. So we would write that P is less than or equal to 30. And then for our alternative would be more than 30% of the registered voters in Santa Clara County voted in the primary election. So we would say that as P is greater than 30. Another example would be if we had a medical trial is conducted to test whether or not a new medicine reduces cholesterol by 25%. The null hypothesis would be the drug reduces cholesterol by 25%. So P would equal 0.25. And the alternative would be the drug does not reduce cholesterol by 25%. So the alternative hypothesis would be P does not equal 0.25. Okay? Now, there are 4 possible outcomes depending on the actual truth of the hypothesis and the decision to reject or not reject. So let's look at what those might be. So my 2 actions are do not reject the null hypothesis and reject the null hypothesis. So if the null hypothesis is actually true, and I choose not to reject the null hypothesis, then I have the correct outcome, and I've made the correct decision. But if I choose to reject the null hypothesis and the null hypothesis is actually true, then I have made what is called a type 1 error. And this is when I've made an incorrect decision. Now, if we have the opposite and the null hypothesis is actually false, and I choose not to reject the null hypothesis, then I will have what is called a type 2 error. And this would also be, if it's an error, then this means I made an incorrect decision. If I choose to reject the null hypothesis and the null hypothesis is actually false, then once again I have the correct outcome and I've made the correct decision. Okay, let's look at some examples of that. So, and before we do that, so the probability of having a type 1 error is called alpha. So this is the probability of having a type 1 error. We'll use alpha. The probability of having a type 2 error, we're going to label as beta. So an alpha, both of these probabilities we want to be as small as possible because they're probabilities of error and they're rarely zero. 1 minus beta is called the power of the test, and we want that to be as close as possible to 1. And increasing the sample size n will increase your 1 minus beta, and we want that as close to 1. So, and your alpha right here, so that is called your power of the test, and I'm not going to write all this stuff down because that takes time. Your alpha, this alpha for your type 1 error, this is the same alpha that we saw with confidence intervals. It's called your significance level, and we will be using that value when we're calculating, when we're doing calculations with our problems. So you're going to see this alpha show up very soon. But just to look at these type 1 and type 2 errors, let's go ahead and show some examples. Okay, so here's some examples of type 1 and type 2 errors. Okay, so the first one would be, so let's suppose that the null hypothesis is that Frank's rock climbing equipment is safe, then that means the alternative hypothesis would be that Frank's equipment isn't safe. That would give us a type 1 error when, if we reject the null hypothesis, that Frank thinks that his rock climbing equipment may not be safe when in fact it really is safe. And the type 2 error is when we do not reject the null hypothesis, even though the null hypothesis is false. And that would be that Frank thinks his rock climbing equipment may not be safe when in fact it is not safe. So your alpha is the probability that Frank thinks his rock climbing equipment may not be safe when in fact it really is. And the beta is going to be the probability that Frank thinks his rock climbing equipment may be safe when in fact it is not safe. Now, if you look at these two errors, we'll notice that in this case, the error with the greater consequence is the type 2 error. If Frank thinks his rock climbing equipment is safe, he'll go ahead and use it even though it's not safe, and so he will be at risk of getting hurt. Here's another example. It says, suppose the null hypothesis is the blood cultures contain no traces of pathogen X. State the type 1 and type 2 errors. So if we have the null hypothesis is the blood cultures contain no traces of pathogen X, then the alternative would be the blood contains pathogen X. So another way that we could write this is that HO would be P does not equal pathogen X, and your alternative would be that the blood culture does contain pathogen X. So in this one, the type 1 error would be that we reject that it's true that there isn't any, that it doesn't contain it, but we reject it, we think it does. And then the type 2 would be that we would reject, we do not reject the null hypothesis, even though it is false. So the type 2 error would have the greater consequence because we would think that the blood does not contain any pathogen when it really does. Okay? And their error is not always going to be your type 2. So another example would be if we had a null hypothesis that the patient has cancer, and the alternative is the patient does not have cancer. Then if we do not reject the null hypothesis, we would get the correct outcome, and the patient with cancer would get treatment. If we reject it and this null hypothesis is true, we would have a type 1 error because a patient with cancer wouldn't get treatment. If the null hypothesis was false, that the patient doesn't have cancer, the type 2 error would be that we reject the null hypothesis and the patient would end up getting treatment for cancer even though he doesn't have cancer. If we reject it, then we would have the correct outcome that the patient doesn't have cancer and so no treatment is needed. In this example, the type 1 error would have the greatest consequence because a patient with cancer would be misdiagnosed and would not get treatment. Any questions about identifying type 1 and type 2 errors and how to identify which has the greater consequence? Okay. do a new board. Okay, so now to get the, if we have a single population mean, then the formulas we're going to use, we're going to have our sample mean. It's going to be a normal distribution, which is going to have the mean of the sample, standard deviation of the sample over square root n, which we've seen this from our central limit theorem, or it's going to have a t distribution using degrees of freedom. We'll use this first one if we have a known population standard deviation, and we're going to use the t-scores if we have an unknown population standard deviation. Now, if we have, and these are for single population means. Now, if we have a single population proportion, we're going to use the formulas p prime, normal distribution, and then instead of mean and standard deviation, we're going to use our p for number of successes, and then our standard deviation is going to be our p prime times q prime divided by n, where p prime is going to be x over n, where x equals the number of successes and n is the number of trials. Or excuse me, it's not number of trials, it's the sample size. Okay? Now, whenever we're doing hypothesis tests, we're going to make some assumptions. So if we have a single population with a mean, we're going to use let's see. So we're going to use the normal. So if we have a single population mean, known population standard deviation, we're going to use the normal test with the t-scores, the z-scores. If we have a single population mean with an unknown population standard deviation, we're going to use the student t-test distribution and the t-scores. If it's a single population proportion, we're going to use the normal distribution with the z-scores. And then we've already seen we're going to use the normal distribution where our mean is going to equal to the mean of the samples, and the standard deviation is going to be the standard deviation of the mean divided by the square root of n, which we got from our central limit theorem. And I've already given you these definitions. Okay. Now it says if sample properties are unlikely, then we're going to assume that the assumption is false. If it's unlikely or a rare event. So most of the time when you are setting up your hypotheses, you're going to make whatever it is that you're claiming to test, you're going to make that to be your alternative hypothesis, and you're going to set whatever the opposite is as the null hypothesis. And then in order to figure that out, you're going to find a p-value, and the p-value is the probability that if the null hypothesis is true, the results from another randomly selected sample will be as extreme or more extreme as the results obtained from the given sample. A large p-value tells you to not reject the null hypothesis. A small p-value is going to be more unlikely the outcome, and you're going to reject the null hypothesis. So let's see what that looks like. So let's do a couple of formulas so that you know how to solve for this p-value, and then we'll plug it into an actual example. So the p-value method. So let's look at basically what they're even talking about here. So what this is saying is that if we have some mean, and we want to say we think the sample mean is going to be, say, here, then we want to know what is the probability that if we do a bunch of tests that our mean is going to fall within this range. It's either going to be equal to this sample mean or it's going to be greater. So that's what they're asking for. Instead of what was originally given, what's the likelihood that the mean actually is going to fall in this area that's shaded rather than where the population mean is stated. And all we're doing with this p-value, is just this area under the curve. And so basically this is what we're doing is we're doing the exact same thing as when we were solving for percentiles. That's exactly what we're doing. It's the exact same type of formula. So to figure this out, we're going to want to get what is called a test statistic, which is just your z-score. And we get that z-score by taking whatever is the sample mean minus the population mean divided by the population standard deviation divided by the square root of n. And our t-scores are going to be the same. It's going to be very similar, and we've seen these formulas before. The t-score is going to be the sample mean minus the population mean divided by the sample standard deviation divided by square root of the sample size. Now, if you remember from Module 6, when we were first introduced to z-scores, the z-score, which is an x value minus the mean divided by the standard deviation. And the z-scores just tell us how many standard deviations away from the mean, how many standard deviations away from the mean that the x value is. And this is doing exactly the same thing. And what this is doing is it's going to allow us to compare different sets of data. And as I'm talking, if anything gets a little confusing, let me know, because I think some of it is a little confusing, but once you can put all the pieces together, then I think it makes a little more sense. So when you are doing, when we did confidence levels, so let's take a look at this. So when we did confidence levels, we had our confidence intervals. We had our confidence level, which was 1 minus alpha, and then the side. And we were solving for this area under the curve. And then this empty space was alpha over 2. We split it. So now what we're going to be doing is Now we're looking for just the opposite. So if I have a two-tailed test, then I'm going to be looking for this shaded area, this alpha over 2. And this is still going to be, all be the same. And if I have a tail to the right or the left, then this is going to, so this would be a right-tailed, right-tailed, and then this one right here would be a left-tailed. But we're using the same basic formulas that we've done before. It's just being presented a little bit differently, and we're looking for a different part of the graph, but it's basically the same. So if I have a two-tailed test, so we'll start with a two-tailed test. So let's say I'm given, so first off, a two-tailed test is always going to have your equal and not equal. And you look at whatever your alternative hypothesis, that's going to tell you what type of test you have. So if you have a equal or don't equal, usually it'll be a don't equal. That's going to be a two-tailed test. If you have your, so this would be like P or so we'll just say P is going to equal some value. If you have we can keep that. No, I'm not going to put next there. So then let's say you have, so this would be your H of A. Then for a right-tiled test, let's say you have your mean is going to be less than some number. This would be a right-tailed test. Then if you have your HA, your alternative, has your mean being greater than some number, this is going to be a left-tailed test. And I'm going to go ahead and change the P to a mean just to keep all of this notation the same. Okay, so if you have an equal or don't equal, you're going to have, it's going to be two-tailed, it's going to be split. If it's less than, it's going to go to the right. If it's going to be greater than, it's going to go to the left. And the way that we solve these, so let's do just some quick examples. And so let's do, and here I'm going to just give you your confidence levels. So for your alpha, so let's say my confidence level 0.90, 0.95, 0.98, and 0.99. Then my alpha would be 0.10, 0.05, 0.02, 0.01. Then for my one-tailed test, my z-values are going to be the probability. We're going to use the probability that x is less than z, which is 1 minus alpha. So those are going to give me 1.28, 1.645, 2.05, 2.33, and I'll show you how we solve all of these, but I want you to be able to see these as a chart. If I have a two-tailed, then they're going to be similar to what we've done before. So if you remember, for a 90%, it's going to be plus or minus the 1.645, plus or minus 1.96, plus or minus 2.33, plus or minus 2.575. And we're going to use the formula. We're going to use 1 minus alpha over 2 when we're solving for z, because we're splitting that alpha onto two sides. If it's 1, we're just going to use the whole alpha when everything's going to be shifted. And then if it's two-tailed, you're going to split it. Okay? So let's do some examples so you can see what these look like. So let's say I have a left-tailed test. So let's say I'm given my null hypothesis is going to be that the mean is going to be less than or equal to 0.43. My alternative mean is going to be 0.43. And then let's say they tell us able to figure out. So let's say they give us a z-value of 2.78. Then in order to figure out what the p-value is, which is, so this is your z here, in order to figure out what this p-value here is, we're going to plug in p x greater than 2.78. Because we're going to use the same sign as whatever's in the bottom. So this should give us 0.0027. So if I have, because I have a z-score, then I can use the normal distribution with a standard normal distribution, which means I can use a mean of 0, standard deviation of 1, and plug in this value where x is greater than 2.78. And then if I calculate that, that's going to give me a percentage of 0.027, which tells me that my p-value is going to equal that 0.0027. Okay, and we can, because we don't know, so remember if we have a z-value, then we can compare the z-value on one piece of graph with the normal standard deviation. So remember from when we did this in Module 6, that if I have a z-score on one graph, I can compare that with a z-score on another graph that has different data. Any questions about the z-scores and how we're figuring out these p-values? Okay. Okay, so now let's do an example. And I think I switched these around. So this should actually be P, this should actually be over here. Did I switch them? I think I did switch them. So if it's going to be greater, it's going to be a right tail. Yep, I've got those switched. I do apologize. So if it is, and you can just look at this intuitively. We're looking for a number bigger that's going to go to the right. So that means that this mean should be bigger, and then this one is going to be going smaller. So that should be that direction. So if I have this here, so if it's going to be on the right, then I'm looking for something bigger. If I'm going to have it on the left, I'm looking for something smaller. And I apologize, I just had my notes. This is the right. Okay, so then if I want a left-tailed test, let's say that I'm given a null hypothesis where the mean is greater than or equal to 0.15. The alternative, so this would be here. So this would be like our z is, let's write this a little better. So this would be like our z for this right one that we just did was 2.48, and what we were given was 0.43. So this is our mean, this is the z that we found, and this is our p-value is in the shaded area. So with this one, we're going to say our mean right here is 0.15. Our alternative says that it's going to be less than 0.15. From the data, we're given an initial z-value. We're going to calculate a minus 1.34 as our z-value. And then we want to know what is the probability that that mean is going to be in that shaded area. So we're going to do the same formula that we did before. So now I'm looking for x to be small. So I'm going to plug that in, that minus 1.34. And that's going to give me a probability of 0.09012. Okay? So that gives me that's going to be my p-value. Now, if I have a two-tailed test, then let's say my HO, let's say it's mu equals 100. The alternative does not equal 100. Given an alpha equals 0.05, alpha over 2 would give me a 0.025. Then to figure out the z value, I'm going to take my mean by sample mean minus the population mean, or the mean of the null, divided by the population mean divided by the square root of the sample. And let's say they give us a standard deviation of 15, a sample size of 30. Then we're going to plug these numbers in. And let's say they gave us a sample mean of 140. So then that's going to be 140 minus the population mean of 100. It also gives the population mean of 100 divided by 15. Over the square root of 30. And then when I do all of that calculation, that's going to give me a 14.6 for my z value. And then I'm going to plug that in to get my p value. So we've got x is going to be greater than 14.6. Which is going to give me a probability of 0. Now, so let's look at what this one looks like. So if I do my graph, this is saying I'm being given a mean of 100, and I want to see if I get a sample mean of 140, and we want this equal so I want to know what this p-value is. Now, because it's going to be equal, we're going to have opposite sides. Let's see. So for our we want to know what's the likelihood that it will equal, that it's not, we're getting a, so we have a population of mean of 100, and our sample got 140, and we want to know what's the probability that it's not going to, the mean is not going to be 100. So we're going to compare, so we got 140 as our sample. Now we're going to compare that to the normal standard deviation with a confidence interval. So if I have a confidence level of 95%, that's going to give me my 0.025 on either side. And then that tells us from when we've done z-scores before that our z-score of a standard normal distribution is going to be 1.96. So there's two rules for rejecting. If our calculated z is greater than our z over alpha over 2, we're going to reject the null hypothesis. We also have if alpha is greater than our p-value, we're also going to reject the null hypothesis. So for this one, so what this is telling us are we got a z-score of 14.6 and the z-score on the normal standard deviation, this was just 1.96, which means that 14.6 is probably way out here. So it makes sense that it's unlikely that if our standard is 1.96 standard deviations away from the mean, and we got a standard a z-score of 14.6, that we're going to be way off of that mean. And so that's why we would reject it. With this one, the alpha was 0.5. So let's look at these numbers. So that gives us that 14.6 is greater than 1.96. So that would tell us to reject the null hypothesis. And then we also had our alpha, which would give us a 0.5. That is greater than our p-value of 0. So both of these would tell us to reject the null hypothesis, which would tell us that the mean, it's unlikely that the mean is going to be 100. Okay, let's look at the two prior examples and see with those. Let's see, were we given an alpha? No. So the first two just showed us how to solve for the p-value and the data so that you can see what those look like. Okay, any questions so far? I don't know that I'm explaining this as clearly as I would like to. but I think it will make more sense when we do example problems. The one thing I wanted you to see is that if it's one-tailed, you're going to subtract the alpha. If it's two-tailed, you're going to subtract the alpha over 2. Okay? So now let's do now let's do some actual problems. Okay, so let's say we're given a normal distribution has a standard deviation of 1. We want to verify a claim that the mean is greater than 12. A sample of 36 is taken with a sample mean of 12.5. So let's look at what does that give us. So we know it's a normal distribution. It's going to have a standard deviation of 1. We want to verify the claim that the mean is greater than 12. And we have a sample of 36. Okay, so our mean 12, and we're given a sample of 36, and we're given a sample mean of 12.5. So now we want to verify, so we've given so this is the data that they've given us, and we're going to have so remember that when we think it might be unlikely, we're going to make our alternatives be what we want to verify. So we want to verify a claim that the mean is greater than 12. So that means I'm going to set up my alternative hypothesis that the mean is going to be greater than 12. So that means the opposite is what we're going to say is our null hypothesis. So we're going to say that we're going to test that the mean is less than or equal to 12. Okay, so now we've been given all of our data. So we have on our little picture, we're looking at, so as you can see here, actually they've already drawn that picture. So we've got a mean of 12, and we want to test, so our sample gave us a mean of 12.5. So we want to test what is the likelihood that we're going to get, if we do a bunch of tests, that we're going to end up with a sample mean of 12.5 or something even greater than that. So then what we're going to do is we're going to take so first we're going to calculate our z value, which is going to be the mean minus the standard, the sample mean minus the population mean divided by the population mean divided by the square root of the sample. So that's going to be 12.5 minus 12 divided by 1 over the square root of 36. And then when I do that calculation, I'm going to end up with 3. So my standard deviation is going to be 3. Now, anytime if they don't give you your significance level, then we're going to assume that alpha is going to be 0.05, which is a confidence level of 0.95, a 95% confidence level. So if you remember, we're going to do, you can look at this is a right-tailed test. So that means my p-value, to solve for that p-value, I'm going to have p-value of x greater than z, and I can set that equal to 0.05. So I want to see if this probability is going to be, x is going to be greater than 0.05 when I have a mean of 0, standard deviation of 1, 0.05. And you can see on this graph, let's see, I think I need to move this over a little bit. See it. So this is showing what when I have an alpha at 0.05, and I want to know what the probability of my value being that z value, which is right here where these two intersect. This is the probability that I'm going to have that 0.5%. So that's going to give me a z value $1.645. Okay, and this will be my z for my null hypothesis. And you could have also done the opposite and put in 0.95 and just change the sign. That would be just the opposite. That will still give you that same point where those two transition. That's still going to give you that same point, but that's just showing that just giving you the 95% is your confidence level, and then on your left and then on your right is going to be your alpha. So now I have my z for my data, which is 3. I have my z for my null hypothesis, so I can use the formula and test it out. Is z greater than the z of my null hypothesis? So this is 3 is greater than 1.645. So based on what we've learned before, that tells us we're going to reject the null hypothesis. Now let's go ahead and solve for the p-value to check. So if I'm going to solve for the p-value, so that's going to be the probability that x is going to be greater than 3. I think I did something wrong. Nope. Oops, this is the other one. Probability x is going to be greater than 3, because I'm coming back here. So before I was looking at the percentage. Now I'm looking for the z is an actual point, so that's why I'm using this one. And then this is going to tell me that my probability is going to equal 0.00135. Then once again, in order to compare this, I'm going to see is alpha. We want to know if alpha is greater than our p-value. So our alpha we were given as 0.05. That is going to be greater than our p-value of 0.00135. So that tells us to reject our null hypothesis. Okay. Now, if you will notice that you could have also calculated your p-value, we could also calculate, so using the z-values and this formula, that is the official way to calculate your p-value because you're using the standard normal distribution. But if you calculate, you could also calculate your p-value. How did I do that? If I take my given mean of 12 and my standard deviation as population standard deviation divided by the square root of the sample. So in this case, this would be our 1 divided by square root of 36, which is 0.166. Then you could also find the probability that x is going to be greater than the sample mean of 12.5, and that's going to give you the exact same calculation. So let's see what that looks like. So if I put in the mean of 12 and a standard deviation of 0.166 and say, what is the probability x is going to be greater than 12.5? Get rid of all of these extra numbers. And we can see that this is, and actually it gave us just slightly different. So both of these gave us 0.13. That these are going to give us similar numbers because of these are the same z-values. So remember that if I have a standard normal distribution, which means that my mean is 0, standard deviation is 1, and it has a z-value of 3, I can have a different graph with a different mean. So this is a mean of 12, and then my value 12.5. This is also going to have that z-value of 3. And that's why these two probabilities for the p-value ended up being exactly the same. So that gives you another way to solve for your p-value. It's the official way will tell you to use your z-scores, but if you also use the original data with the sample mean, then you should also end up with that p-value. So that gives you a second way of finding it. So, and then you've also got two ways to determine whether or not you should reject the null hypothesis. The first one is to take what is the z-score from your data, the data minus the given population versus the z-score of using your significance level, and you can compare that. If it's greater, then you're going to reject it. Same thing with if you have your alpha. If that's greater than your p-value, you're also going to reject your null hypothesis. Any questions so far? Okay, let's do another example. Okay, so here's another one. This is the baker example. So with this one, so a baker claims that his bread height is greater than 15 centimeters. So that means we're going to have our null hypothesis. Our null hypothesis is going to be that the mean is going to be less than or equal to 15 centimeters. And our alternative is going to be that it's going to be greater than 15 centimeters. We're going to be given a sample size of 10 loaves of bread. The sample mean came out to be 17 centimeters, and we have a standard deviation of 0.5. It's a normal distribution. So that means if we have our standard deviation for our sample is going to be the standard deviation divided by the square root of the sample. That's going to give me 0.5 divided by the square root of 10, which is going to equal 0.16. Okay, so then we're going to have an alpha is going to be 0.05. So, and we solved this the last time, that gave us a z-score of 1.645. And then we're going to do our z-score for the data, which is going to be the mean minus the sample mean divided by population over the standard deviation divided by the square root of n. So that's going to be 17 minus 15 all over 0.16, which is going to give me that's right. Okay, which is going to give me a z-score of 12.5. So then I'm going to find my p-value, which is the probability that x is going to be greater than 12.5. So if I plug that in with 0, 1, 12.5, that's going to give me a probability of 0. So that tells me that, so if I have my alpha is 0.05, it's going to be greater than 0. So that's going to tell me to reject the null hypothesis, that which would tell me that the loaves of bread are likely, the height is likely to be higher than 15 centimeters. And then we also can do our test with our z-scores, which for 12.5 is much greater than 1.96. So that would also tell us to reject our null hypothesis. And then we can also see, like we did before, where we can compare the graph. So if I use the mean of What's the mean of 15, the standard deviation of 0.16, and I wanted to know if the x values are going to be greater than 17. Once again, that gave me a 0 probability. Okay, any questions? Okay. Okay, and so what this means, if I'm rejecting the null hypothesis, then that just tells me that the data does not support the null hypothesis, and so that we would conclude, it says that the data favors the alternative hypothesis, so we would say it's more likely that the height of the bread is going to be greater than 15 centimeters. Okay, let's do a new one and do populations. Now for populations, we're going to use instead of using the p-value method, we're going to use what is called the traditional method. In our test statistic, which is your z-score, we're going to use p prime minus, so that's your estimated probability of success minus the population success divided by the square root. Population, the success minus times the failure divided by the sample size. Okay, so this is from Boston University. So your book gives you practice problems with using population, but it doesn't really tell you how to solve them. So here is, this is a good website from Boston University. Oops. And it's kind of a long website, but if you also do a search for one sample test of proportions or hypothesis testing for proportions, you're going to get some good resources. But I wanted you to be able to see these. So let me see if I can't get this stuff out of the way so you can see this. So here we go. We have an example. So let's say, so in order to do proportions, we're going to use, remember, our p prime is going to be the number of successes divided by our sample size. We've got our formula for our test statistic, and we're going to use the same rules that if z is greater than z of alpha over 2, we're going to reject the null hypothesis. And let's go ahead and do a sample example problem. So let's say we want to know the proportion of children living near a lead smelter who have colic. The prevalence of colic in the general population is approximately 7%. 7%, and a sample data from a study on the effects of lead exposure gave a, so let's see, I'm looking at interest of time, so I'm not going to read the whole statement so that we can work through this whole problem. So let's say we're given a sample size of 124. We have the number of successes or the number of cases of children that had colic is going to be, so let's say our X is going to be 23. our population. So our probability of success for the general population is 7%. So that's going to be 0.07, which is going to make the probability of failure to be 1 minus 0.07, which is going to be 0.93. Okay, so then we have, so here's our hypothesis. We can see it's written out here in this text. So we're going to make our null hypothesis to be the proportion of colic among children living near lead smelters, which is 0.01. So we're going to say, give our P for our null hypothesis is going to be 0.07. Make the alternative to be the opposite. We're going to say it's not going to be, it's going to be something different than the general public prevalence. We're going to have a significance level of 0.05, which means our confidence level is 0.95. And then from what we've done before, that means we're going to have a z-score of 1.96. And because these are equals, we know it's going to be a two-tailed test. So that means I'm going to want to know my alpha over 2, which is going to be 0.025. So then we're going to solve for our z statistic, which is going to be p prime minus our PO over the square root PO QO divided by n. So, and I didn't solve, so our P prime is going to be x over n. So that's going to give me P prime is going to be 23 over 124. So that's going to give me a P prime of 0.19. So that's going to give me a z-score of 0.19 minus 0.07 divided by the square root of 0.07 times 0.93 divided by n, which is my 124. And that's going to give me 0.12 divided by 0.0229, which is going to equal 5.24. So then if I look at my, see if my z is greater than z of alpha over 2, that means I've got 5.24 greater than 1.96. So that would tell me I'm going to reject the null hypothesis. And then if I wanted to, I could also, because I've got my confidence level, I could also find the confidence intervals, which we've used before, and that would just be P prime plus or minus our z alpha over 2 square root P prime Q prime over n. So my Q prime, I've got P prime equals 0.19. So that means my Q prime is going to be 1 minus 0.19, which equals 0.81. So that makes my confidence interval be 0.19 plus or minus 1.96 times the square root of 0.19 times 0.81 all over 1.24. So that's going to end up giving me a confidence interval of 0.12 and 0.25. So what that would tell us is that we can reject the null hypothesis and conclude that the prevalence of colic among children living near lead smelters is different from the general population of 7%. We can also say that we have 95% confidence that the mean population value is going to be between 12% and 25%. So any questions about anything that we've gone over? I think the main thing to know with the hypothesis test for finding for a single sample is to know what your formulas are and what the rules are for when you reject your null hypothesis and when you're going to not reject it. Okay. So it looks like that covers everything I can do. Looks like I can have time. I can do one more example. So let me pull out another example for you. Any questions about the example with the proportions? Because I kind of rushed to that one a little bit. So we went over the formulas, but I didn't really go through all of the words. If you also, WikiHow also has some good examples on how to use the formulas. But I think as long as you know to use that Z-statistic formula and you're using the binomial distribution for your proportions like we did within the last module, then I think you'll be fine with that. So let's go ahead. We have a little bit of time left, so let me do one more. Okay, so with this one, we're going to have that Jeffrey is an 8-year-old. He has a mean time of swimming at 16.43 seconds with a standard deviation of 0.8 seconds. So his dad thought he could swim faster if he had goggles, so he bought a pair of goggles, and then his mean time became 16 seconds. Then he did 15 swims, so that'd be our sample size. For Jeffrey's mean time, okay, so so I bought him goggles, and then he did 15 swims, and then this time his average mean was 16 seconds. So then we have to hypothesize. So he hypothesized that the goggles are going to help his son to swim faster. So then we want to set this up as a hypothesis test. So we're going to say our alternative hypothesis is that the mean time is going to be less than to 16.43, and that our null hypothesis is going to be that the mean is going to be 16.43. So because it has a less than, then that tells us it's going to be a left-tailed test. So we've got a mean of 16.43. We've got an average mean of 16, which is less, and we want to find the probability that if he uses the goggles, the probability that his swim time is going to be 16 seconds or less. So that tells us it's going to be a left-tailed test. We're going to have a significance level of 0.05, which means that's going to give us a z-score of 1.645 from what we've done before. Now we're going to plug our numbers in. So our z-score that we're going to calculate, so this is our z of alpha. We're going to have the mean minus the population divided by the standard deviation over the square root of the sample. I guess I should put this over here. So that's going to be 16 minus 16.43 divided by 0.8 divided by square root of 15. So when I plug all of those numbers in, I'm going to end up with a minus 2.082. So when I'm looking to compare these, the standard deviation, if I have 0, so that's going to be a plus or minus 1.645. And we ended up with a minus 2.08. So our first thing tells us that we want the absolute value of z. We're going to see if that is greater than the absolute value of z over alpha. So this is another thing to remember, is that you want the absolute values because we're looking at, we want to go the opposite direction. So that's going to end up making your numbers different. So if I have the absolute value of a minus 2.082 and compare that to the absolute value of a minus 0.645, we're going to see that that is greater. So we're going to reject the null hypothesis. So if you can remember just to use the absolute values, that's going to be easier. Or when you have a negative z, you can also say if you have a negative z, you switch this greater than or equal sign. Because whenever you multiply by a negative and you have inequalities, the inequality flips. But I think it might be easier if you just remember to use the absolute, then you can keep this in the same direction each time. So what that is telling us is that my z-score of my alpha is here at minus 1.6. My z-score of 2 is much smaller, so that would mean that we would expect that his speed time, or the mean of his speed time, to be much less than the given mean of 16.43. Then we can find our p-value by plugging in the probability that x is going to be less than minus 2.082. When we have a normal distribution, normal standard distribution, and we can see that our probability is really small. And remember, if our probability is really small, then we're going to reject it. And we also have our rule that if alpha is greater than our p-value, we're also going to reject the null hypothesis. So our alpha was 0.5, which is greater than our 0.187. So that also tells us we're going to reject the null hypothesis. So our interpretation, or the way that we can say this, is that if the null hypothesis is true, that there is a 1.87% probability that Jeffrey's mean time is 16 seconds or less. Because that is such a small percentage, it's unlikely to have happened randomly. It's a rare event. So we're going to reject the null hypothesis because the probability value is small. And then we can say our conclusion is at the 5% significant level, we conclude that Jeffrey swims faster using the new goggles, and the sample data gives sufficient evidence that the mean time is less than 16.43 seconds. Okay, so that should be everything for hypothesis testing with a single sample. Any last questions before we wrap up for today?
I hope you found this to be helpful. Be sure to like and subscribe to get the latest videos by Caz Academy. See the links below for additional supports and resources, and I'll see you at the next video.